In this section, we'll study Krylov subspace methods for the solution of symmetric positive definite algebraic systems. Let's begin with a definition. A is a square metric. It is said to be positive definite if the quantity x transpose AX, in detail we can get this. The quantity is positive for every choice of non-zero x. In this section, we'll try to solve this form of a linear system where A is symmetric positive definite. Krylov subspace methods update the iterate in this way. Beginning from an initial guess x0, now we try to get a new iterate from the old one by adding the search direction scaled by the step length. Different methods differ in the choice of the search direction and the step length. In this section, we'll consider the gradient descent method, the conjugate gradient method, and preconditioned conjugate gradient. In the next section, we'll study the generalized minimum residuals, GMRES, for the solution of linear systems AX equals B with arbitrary non-singular square matrices. Okay, now we reformulate this problem AX equals B in this way. Now once A is positive definite, then now F eta is a vector in Rn and defined in this way. Now minimization of this function is the same as solving this problem AX equals B, and it's positive definite, so it's quadratic, and assume it's one-dimensional vector n equal 1, then it's a form of 1/2 and A eta squared minus B eta, and that is F eta. Now, once it is optimized at minimum, then at the minimum, the derivative must be 0. So that F prime eta, which is same as now A eta minus B, so it must be 0. We are taking the derivative with respect to eta, so we reach at this equation. When n is 1, then that is exactly same as this equation. But even for arbitrary n, you can prove this one the same way. In detail, you can compute the derivative and you can reach at that one. So eventually, this problem is equivalent to solving AX equals B. Let's begin with the gradient descent method. The gradient descent method is also known as the steepest descent method or Richardson method. We first get the gradient and Hessian of the function f, and we try to use f prime and f double prime. Practically, this is a gradient of f that is Hessian, but we are using the notation prime and double prime. Now f prime eta is A eta minus B, and double prime must be the metric A, Hessian. Now xk plus 1 in the update formula, xk plus 1 is same as xk plus alpha k pk. So f of xk plus 1 is same as that one. Now we are using Taylor's expansion. Then now f of xk, alpha k, and gradient of f dot pk. And here in the second term, we stop. In fact, for this function, third derivative doesn't exist. It's now constant. And there's alpha k squared over 2, and we have this Hessian and pk. So that is the Taylor expansion. So we may try to write down this equation in this form because A is bounded. So we may say that this is order of alpha k squared when alpha k is small. So this can be written in this form. Now the goal in the algorithm is to find the pk alpha k such that at the new iterate, the value, function value is smaller than at earlier, the xk. So at due iterate, due vector, the function value must be smaller. Okay. Now, very simple choice for that is this portion is smaller than 0, then now that will be satisfied. So we try to find pk such that this portion is smaller than 0. Then this inequality must be satisfied. And for this one, right now, this is positive definite, so that this is non-negative. In fact, it's non-negative. Or even though it is not non-negative, we may try to get alpha very small, then that will be very smaller than this term, so that once it is smaller than 0, then this side will become smaller than this one. Okay, so that is the condition. Now the choice is for P, we try to get negative of this one. So negative of the gradient. So pk is minus f prime. And practically this one is b minus axk. That is a residual, kth residual. That's the choice for the gradient descent method. And negative gradient is chosen for the search direction. Once this search direction is chosen, then now what we have to do is to determine the stem length. Here is an optimal technique for taking stem length. We try to determine alpha k such that this alpha k is the minimizer of the function. Once we consider this part as a function of alpha, then among every possible alpha, we try to choose the value such that this one is minimum. Okay, so such alpha k is optimal. How can we get it? This is quadratic. Again, we try to use the calculus technique. We differentiate with respect to alpha of the function, and when alpha is alpha k, then because alpha k is the minimizer, the value must be 0. So we do practical computation. Then there is gradient at the point, and then now pk, alpha derivative, there is coefficient. So gradient of that dot pk. Of course, after that, alpha must be replaced by alpha k. Now, earlier we know that f prime eta is a eta minus b, so that f prime, this vector is same as a times this vector minus b, and pk. We expand, so that from this one, of course this is negation of residual, so that minus rk, and let's write down here, that's minus rk dot pk plus alpha k pk a pk is 0. So we move this one to the other side and divide by this scalar. So we reach at alpha k, and in this way. That is optimal. And this way of getting the step length is quite universal for almost all methods. They are taking alpha k by using this formula. So earlier we decided the search direction, which is negative gradient. Now, by using this optimal technique, we try to get alpha k. And with this choice, the gradient descent method will be formulated, and once it is solving the problem, now the convergence can be analyzed. X minus xk, x is the true solution, and xk, kth iterate in L2 norm, is bounded by this quantity. Kappa A is the condition number of A to the k, and the initial error. So each iteration makes this reduction. Now, once we try to get the number of iterations required to satisfy a given tolerance, epsilon, okay, so that we have to make this quantity bounded by epsilon smaller than or equal to epsilon, and then we try to control this term and bounded by epsilon, and then automatically this term will be bounded by epsilon, right? So we try to solve this inequality, then we reach at this one. So given the choice of tolerance, and if we know the condition number of A, then the required number of iteration is at least this quantity. So that, and here the convergence, the number of iteration is order of the condition number. But if you organize an algebraic system, for example, from some network, like solving the partial differential equations, and if you partition the domain and the grid points are selected, then eventually the PD will make a network and connect it. And here at some point you are making relation to the neighboring point and so on. So out of this one you can get now AX equals B. And for such algebraic system, once you choose, for example, over there endpoint, again not 10, and endpoints, and also vertically n, and then the condition number of A is usually n squared. And once you choose, for example, 100 points in each direction, then the condition number of the corresponding algebraic system will be order of 10,000. So it's a very large. So number of iteration must be very large to get reasonable convergence. the gradient descent method is not so fast. It's slow. Okay, here we have new method, conjugate gradient method. Now in this method, now we try to find the search direction so that they are conjugate. That means the search directions Pi, Pj satisfy this equation. So along with that, with respect to the metric, this dot product in the product is 0. So for each search direction, they are orthogonal with respect to this metric. Of course, in each iteration, alpha k will be chosen to be optimal. We consider this optimal strategy here by using calculus technique. We try to get alpha k such that this function is minimized. Okay. So we want to get the search direction satisfying this equation. The search directions are conjugate. Here is the algorithm. This is very basic form of the conjugate gradient method. Okay, I'll explain this one step by step. Okay, now initial guess for the solution and epsilon for stopping tolerance. These are given. Then in the beginning, an initial residual and initial search direction P0 from R0 directly assigned. And here alpha k, that is the optimal choice. And we already derived this one. Along with this alpha k, for the given search direction, we update. Now, we try to make rk plus 1 the residual. By definition, this is the same as b minus a xk plus 1. Right? But rather than this one, we try to get this way. The reason is, in the beginning, we may make this computation, metric vector computation, and then we save it into an array like that, and then once it is required, then we use it. So here we can use it also. You can use here and you can use here. So along with that, we need only one metric vector computation, and everywhere else is a vector-vector computation. Metric vector computation is way more expensive than vector-vector computation. Now, if you try to get the residual by using the original formula, then it requires another metric vector computation. It's expensive, so that we'll try to use this formula. Of course, they are the same. We see quite easily. Okay, over there we'll figure it out, and the same. And the main purpose, main goal is to make it not expensive, so that we try to reduce the number of the metric vector computation. So that's the reason we are using this formula. And after getting new residual, once new residual is relatively small with this ratio epsilon, then we stop. Otherwise, now we try to get due search direction for the next iteration. So if we make this one, and that is linear combination between the residual and the earlier search direction. And along with the beta, the weight, we try to get here new search direction. But the beta can be decided in this way. So there is some mathematics for this one. Let's go down and let's try to figure out step by step. Okay, for this residual computation, now RK is this one by definition, so that RK plus 1 must be B minus AX plus 1. Now, but this K plus 1 from this second equation is XK plus alpha K PK. So we can replace this term with that. And now expand, then B minus AXK and minus alpha K APK. That is now residual, the previous residual. So RK now minus alpha K APK, which is exactly this one. Okay. Now alpha K in the first line is optimal. We already saw that. Also, it satisfies now RK plus 1 PK equal 0. You can easily check here. Now RK plus 1, okay, let's try to do that. Okay, now here RK plus 1 dot PK. What is RK plus 1? That one, which is RK. Now there's minus alpha K and APK. Wait, okay. Alpha K APK and PK dot the product. Then that's same as RK dot PK and minus alpha K, a constant, and here PK dot APK. Okay. Now look at over there, and if we try to put over, this must be 0 because alpha K is given in this way. So if you are using this quantity over there, then this bottom portion will be cancelled with this one, and R dot PK minus R dot PK. So that must be 0. So that is the choice alpha K, this quantity, is not only optimal, and with this alpha K, now the new residual and old search direction are orthogonal. It's a wonderful property. Now, also, finally, PK plus 1, APK is 0. In fact, PK plus 1 is in this form for beta K, and we try to match this equation, satisfy this equation, then the choice for beta K must be this one. Okay, let's figure it out. And PK plus 1 is now RK plus 1 and plus beta K. Oops. Now beta K, and then here PK and A, okay, dot A PK. Then for that one, now we can okay, again that is multiplied so that RK plus 1 dot A PK and here plus beta K, and then here pk dot a pk. We try to make this one 0. Then beta k, move this one to the other side, divided by this quantity. That is exactly this one. So the algorithm is designed to satisfy now this equation and that equation. And earlier, and we try to get the search direction conjugate. For every search direction, they are conjugate. But during the iteration, we cannot make that. And now only pk and pk plus 1, just the consecutive, the search directions are conjugate. And only we try to make that. And with this good property, now even though it is only local conjugate, and we can prove this theorem. And the search directions and the residuals satisfy the orthogonality. Okay, for every search direction, and now they are conjugate, completely conjugate. And furthermore, and residual are orthogonal each other. This is really fantastic property. Of course, here for each stage, after m iteration, the P0 to Pm and R0 to Rm, and now R0 and AR0 and so on. This, the vectors, if we consider span of these vectors, then they are all the same. These are called the Krylov subspaces. As m increases, the subspace is enlarged and becoming bigger, 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 but each stage it is making a subspace, which is called Krylov subspace. So the method is like expanding the Krylov subspace and then try to find the search direction and having this property. Every search direction, for all search directions, here they are conjugate, and also residuals are orthogonal. With this wonderful property, now we can say that at some stage, after m iteration, m is larger than, m is smaller than or equal to n. M can be n. And axm equals b, which means that after m iterations, the algorithm completely converges, so that there's no other error. Just xm becomes the true solution. And also, the convergence rate, the error reduction rate is given along with this one. So case stage, the error measured with a norm. So that means that, for example, now x minus xk, a norm scared. That one is the same as this one. Now, okay, x minus xk, and here transpose a and x minus xk. That's the definition. Along with this a, with respect to a, we measure the norm, and a norm at the k step, kth iterate, for the kth iterate is bounded by this quantity and initial error. So each iteration is reducing the error with this factor. Now, we can try to get the required iteration number to reduce the error by a factor of epsilon, so that we put here epsilon in this way and try to solve this inequality, then we reach here. So number of iteration required is now order of square root of condition number. Once we consider the network problem, and here, and then n is now 100, then there will be the condition number is about 10k, 10,000. Now, for that problem, now here, this k is order of 100 because the square root of 10,000 is 100. So then iteration count required for solving the problem is way smaller than that of the gradient descent method. So it's way faster. But in any case, m iteration later, the method should converge, completely convergent. Okay, we can simplify the conjugate gradient method using the properties and identities for the method. We can derive a more popular form of the conjugate gradient method. It's slightly faster, about 5 to 10% faster. So that this is quite popular form of the conjugate gradient method. Okay, here this row notation appeared, and R and P, and rho is now the residual norm square. And here we have that. Okay, here RK dot PK, and earlier, okay, let's go back to the original form. There's RK PK. It's optimal choice of alpha. And for this term, we can simplify in this way. RK PK. Now PK is from, okay, where is it? Okay, from this one. Now once rather than k plus 1 is k, then there must be rk and beta k minus 1, pk minus 1. That's exactly this one. And rk pk. So there's rk. Now rk pk minus 1 dot product. So we have here plus beta k and rk dot pk minus 1. But earlier we saw here rk plus 1 pk dot product is 0. So we are using that, and we can ignore this portion. So we reset that one. So we are using here now row notation. In this way, okay, we can change it. Now again, for beta k, exactly the same way. Okay, now when we try to get beta k, here, originally the quantity is given in this way. Now we keep this portion, that is kept the same. Now for that one, and p dot, okay, for that one, okay, we can use over there p dot apk, p dot ap, that is same as rho over alpha. So that this portion is replaced by alpha over rho. Okay. Now, from here, apk alpha k, that one. Okay, let's try to find this term. Okay, here we have that one. So this is same as now rk minus rk plus 1. So along with this one, now we have rk plus 1 here, along with the negative this one. Okay, negative of that one is exactly the same as rk plus 1 minus rk, that is here. And rho k remained here. And we already know that Now rk plus 1 dot rk is 0. In the theorem, we considered it here, right? So that ij are different, then they are orthogonal, so that the dot product must be 0. So this dot product will be 0. Remainder part is rk plus 1 dot rk plus 1, which is rho k plus 1. Okay, so that here beta k is this one. And we make here rho k plus 1 to be the rk plus 1 norm squared. And then beta k is chosen and use it for this update of the new search direction. So it is exactly same as, mathematically, same as earlier one, but it's simpler, and people like this form, much more popular. Let's see an example. The metric, and right hand side of B, and initial x0 is 1, 1, 1. For that one, we implemented the second version of the conjugate gradient method. And after one iteration, this is x1 and r1, the residual. After two iteration, we have this x, and this is the residual. After three iteration, this is the exact solution, and residual is 0. So after three iteration, it converged completely. And earlier, we saw that. And for some m, which is less than or equal to n, axm must be b, which means axm must be the exact solution. In this case, x3 is the solution. The conjugate gradient method converged completely in three iterations. The CG method was originally developed as a direct solver, because after n iterations, we may consider it as a direct solver. However, if n is, for example, order of millions, larger than billion, then now do we have to run billion iterations? No, we don't have to do that. We have to make the algorithm converge very fast, and then we try to enjoy the fast convergence, and we may stop at some point with the error tolerance, epsilon. You can choose, for example, 10 to the minus 7. At the point we can finish solution, then the accuracy is good enough, and the solution will be very useful. That's the this is one more step. We have to make the CG method faster. Remember, the condition number is critical factor, and then now number of iteration required for some tolerance is, so that the k is here order of the square root of condition number of A. We have this theory already. So once condition number of A is smaller, and if we do something such that the condition number becomes smaller, then we can enjoy in fast convergence. That's the idea of preconditioning. First, we try to choose a metric M. It's spectrally similar to A and easy to invert. And we multiply its inverse, assuming the inversion is easy. Okay, this is easy. So M inverse A is multiplied. Then, now, if M is similar to A, then M inverse A will be around identity, near to identity. so that condition number of this matrix will be way smaller than original condition number. If you can do, then now convergence will be much faster. For the network example, now the number of iterations required is order of 100. But if you can choose good M such that this system has condition number, for example, now order of 10 or way smaller than 10, then now the number of iteration is really way smaller. So square root of 10 will be around 3 and 4, which means that you can get the solution after a few iterations. So that is the idea of preconditioning. Okay. In reality, in practical implementation, you don't have to compute M inverse, and you don't have to multiply in this way. The algorithm can be modified such that, and eventually the algorithm is solving this system. But we never multiply an M inverse to the system. Okay, look at this preconditioned CG method. Now, for your convenience, I made the pseudocode along with complex value, the metric and vector. So that star indicates the transpose complex conjugate. For real value, the system, the star means just transpose. So it is dot product. Okay. Here we have the residual computation. This one is extra. From R, we try to get Z by solving this linear system. And in each iteration, you have to solve this one. And now here Z is used for such direction, and also rho is computed in this way, along with not R only, Z and R dot product. Everything is the same. Only difference is this one. From R, we try to get Z by solving this one, and so it must be easy to solve. You may try to choose, for instance, tridiagonal matrix, and original matrix will be almost full or widely, non-zero components are widely spread, so that it's not easy to get the corresponding M. However, if you try to choose around the diagonal and banded matrix, okay, I'll try to visualize here. There's matrix A, and then main diagonal, and then below, up, and let's try to choose this one to be M. Then even though you choose this small portion of A, now this is easy to solve because it's tridiagonal. And along with that, in many cases, you will enjoy very fast convergence. So that is really good preconditioning. So this is difference. And also when you compute rho rather than R dot product, now along with G, you are making dot product. Only that's the difference. And if you do this way, then that is exactly the same as solving this preconditioned system. And with a good choice of M, you can enjoy much faster convergence, much better. Okay, that's the end of the section. Thank you.